This is part 3 of 3 parts for lecture 2, and what I want to discuss here is some important components of statistical power. So before I begin, let me share the document with you so that you can see that and not me. And what I want to talk about here is statistical power and its role in null hypothesis significance testing. Statistical power is pretty simple. I know we're jumping ahead of everything because I haven't even talked about inferential statistics or hypothesis testing, but I want to give you this concept of statistical power because, as I say in my notes, it's a central unifying concept. And this is particular to frequentist statistics as opposed to Bayesian statistics, something I will discuss from time to time during the class. But for the most part, what we talk about in this 611 course is frequentist statistics. So statistical power is the power that you'll reject the null given that it is indeed false. So this tells us whether it's kind of like the probability of success, all right, given the fact that we have to reject the null in many instances in order to achieve what is called statistical significance at the 0.5 level or below. And because of that, we oftentimes want to know whether we've adequately started out with a fighting chance to reject the null. So let me tell you what the statistical power components are so that you have a better understanding about what's going on. All right, so first, statistical power is a function of 3 things, but it turns out that it's more complicated than just these 3. So the first thing is sample size. Sample size, so this is really a proxy for the stability of our estimate. Now, I showed you before in my little application, I showed you that as we increase the sample size, really it's not changing the standard deviation at all, but it will change the standard error. And that means that we have a little bit more precision in our estimate. So sample size serves as a proxy for the stability of our estimate. And that proxy comes from the law of large numbers, that as we increase, as our sample size approaches infinity, our sample parameter approaches the population parameter. Okay, and so that's really what we want, is we want to get population parameters to the best of our ability. So sample size, as sample size increases, power increases. The next thing is effect size. So effect size is how big of an effect have you created? And here the easiest way to appreciate this is with Cohens D. It's one measure of effect size. So what we have is Cohens D is nothing more than the difference between 2 means. So let's say you have a treatment group 1 and a non-treatment group 2, and you want to say that the treatment group 1, is going to be better off, right? Have higher means. So they're happier than the comparison group. So the numerator would be positive. The more positive the numerator, the larger the effect size. It's the denominator turns out to be a little bit more difficult because a lot of people ignore that. So what is the S star? S star is short for pooled standard deviation, or the standard, sometimes it can be the standard deviation from the group that's more generalizable, like the comparison group. So for our purposes here, I'm going to use the more complicated one. And here's the pooled standard deviation. I'm going to expand this just a little bit. So the denominator is S1 squared. Now we know what S squared is now. S squared is variance, right? So if you take the 2 variances of each of the groups and divide by 2, you're essentially averaging the variances, and then you take the square root of that. And the reason why we take the square root of the average of the variances is because, remember, variance is not what we want when it comes to comparing to our original metric, because variances are in our original metric squared. So if this is in measuring in height, and I wanted to, I gave some great drug to these kids to make them grow taller, and another group of kids in the comparison group, they didn't get the drug, then the numerator would be height, and in the US it would be height in inches. And we'd want to divide that by inches, not inches squared, because D is a metricless unit. It's actually D is in Z scores. So it's would be inches over inches. And that's the reason why we take variances. You average the variances, and then you take the square root of it, and you get a standard deviation. Okay, now, what is it about Cohens D that helps us figure this out? Well, Cohens D is important because it tells us that, one, it's a measure of effect size. The larger the effect, the greater the power. So we can either maximize the difference between the groups, make our treatments really, really strong, or make our two groups as different as possible. So one is, if we don't have much faith in our treatment, we can have another treatment, an alternative treatment, that might be known to be really harmful. In that case, that would maximize the difference between the two groups. But it's the denominator that turns out to be the real sticky issue. And now, why is that? Because when we start looking at effect size, you start realizing that the most important part of Cohens D is not in the numerator. True, the numerator is important, but what's really important is the denominator. Now, why is the denominator relevant here? It's because, as I said before, if you learn nothing else, learn something about variances, because reliability is nothing more than a ratio of variances. Now, what does that mean? Well, the ratio of variances, according to Fred Lord, is we get this idea of rho, reliability coefficient, which is a ratio of true score variance, the variance of the construct of interest, divided by the observed score variance. Okay, now, why is that all of what we're interested in? Well, remember my variance equation that I had before about observed equals, right, that we have residuals, and I can show you this from our previous equation. What I was trying to show you before is this equation of variances. And this equation of variances is something that you're going to see often. So residual variance, or error variance, is nothing more than the observed variance and expected variance. Okay, let's see why that's relevant. If we go down here, we have this idea of a summation model, that there's really three components. There's observed score variance. That's what we see. That's what, and then there's true score variance. That's what, according to Omniscient Jones, really exists. And then there's error variance. Okay? Now, reliability is nothing more than a reflection of how much error we have. So if you have observed score variance as the denominator, it's true score variance over true score variance plus error. So as we have more error in our observations, what happens? Well, what happens is we increase the amount of observed score variance, okay? Because here, this error variance increases, our reliability is going to be lower, okay? We're actually, if you use poorer measures, you have more of this error and you have more observed variance, okay? Now, I told you that variance is king. We need to know variance. But why is that a problem? Well, let's go back up here. What happens when we start increasing the denominator? If we increase, now granted, this is a numerator right here because we're averaging them, but what happens if we increase both of these? Because we have lousy measures for the outcome for both X1 and X2 groups, right? So for both groups 1 and group 2, we have the same outcome measure, and it's not a very good measure. So there's a lot of error variance in here. So these are observed score variances. As these guys get bigger, right, when you average two numbers that are bigger, this whole denominator gets bigger. Well, what happens when the denominator gets bigger in this fraction? Well, D goes down. Okay, so what I'm trying to show you here is that variance matters. Variance creeps into all of these different things. So do measures of central tendency. Okay, that's why you need to know these things. Measures of central tendency, measures of dispersion. But now when Cohens D, as an example of effect size, when the effect size goes down, your statistical power goes down. Okay? When we have lower statistical power, you have less likelihood or less probability, or lower probability of success in finding effects in your study. Okay. And then the other thing that we can talk about is alpha. The problem is we can't talk much about it because for the most part in social and behavioral sciences, alpha is set a priori at 0.5. Okay, so we really have two things that we can worry about: sample size and effect size. And unfortunately, the field, for the most part, has paid more attention to sample size. But when you're done with this class, you're going to see that you get way more bang for your buck by comparing and actually paying attention to effect size. So this is the more advanced material, and this is just an example of the type of stuff that I'm going to be talking about in this part 3 of every week's lecture. It's optional. You may stay for it if you like. I would like more people to stay. Most people in prior semesters have stayed because I talk about all sorts of examples with this, and it really does pull together the material. Again, though, I don't hold it against you if you have to go. So thank you. This is lecture 2 in 3 parts. And following this, at some point, I'm going to start posting things about lecture 3. So thanks for paying attention.